Okay, today we're going to be discussing systems of linear equations in 3 variables. I want you to remember that we just talked about system of linear equations in 2 variables. So remember when we had 2 variables, we needed 2 equations. Now we have 1, 2, 3 equations, but we have 1, 2, 3 variables, x, y, and z. This first system is super easy to solve because it has a 2 by 2 system hiding within the 3 by 3. If we look at the last 2 equations, here and here, we can see that we just have 2 equations and only 2 variables, y and z, because x happens to be missing from those 2 equations. So what we're going to do is we're going to use elimination to solve the little 2 by 2. That will tell us what y is and what z is. Then, in order to find x, we'll have to use the first equation because it's the only equation that contains x. We'll replace y and z, and then we will solve to then find x. So using elimination on the bottom 2 equations, we can either eliminate y, getting a 6 and a negative 6, or we could eliminate z using 10 and negative 10. I personally like the number 10 better than 6, so I'm going to go ahead and eliminate my z's here. So I'm going to choose to multiply that middle equation by 5. That's going to give me a negative 10z, which means I'm going to multiply my bottom equation by 2 to get my positive 10z. So multiplying the entire middle by 5, I obtain negative 15y minus 10z equals negative 25. Multiplying the bottom by 2, 4y plus 10z is equal to negative 8. Now, when we add the 2 equations together, the z's eliminate, and we're left with negative 11y is equal to negative 33. Dividing both whole sides there by negative 11, we find that y is in fact equal to 3. Now, in order to find z, you can either use the original equation 2 or the original equation 3. I'm going to grab the bottom equation, and now I'm going to replace that y with a 3. It now says 2 times 3 plus 5z is equal to negative 4. 2 times 3 is 6, so we have 6 plus 5z equals negative 4. Solving this equation for z, subtract 6 to see that 5z is equal to negative 10. And then when I divide by 5, z is negative 2. To finish, we still need to solve for x. And like we said before, we're going to grab that first equation, the only equation that contains x. We're going to replace the y with a 3 and the z with a negative 2. 3x plus 3 plus 2 times negative 2 is equal to negative 4. So this 2 times negative 2 is negative 4. When I add that to 3, I get negative 1. So 3x minus 1 equals negative 4. Add 1 to see that 3x is equal to negative 3. Then when we divide by 3, x is now equal to negative 1. Normally, we write our answers as points, x, comma, y. Now we're going to write them as triple ordered pairs, and it needs to be in order. So this time it will be x, comma, y, comma, z. Starting with x first, negative 1, comma, y, 3, comma, z, negative 2. And we still put those in parentheses just like we always put points in parentheses. And the answer that I'll circle looks like this. Moving on to a harder system, like the one that we see here, what we're going to want to do is we're going to want to create a 2 by 2 system like we had here. so that we can then solve for the two variables in the 2 by 2 and then plug that back into any of the equations to find that third variable. I personally just like to eliminate x so that we have two equations with y and z. And because I see a 4x in this first equation, it would be nice if I had a negative 4x right here. Then if I were to add those two together, the x's would eliminate, giving me one equation that only has a y and a z. So to start, I'm going to copy the first equation exactly as it is. 4x minus y plus 2z is equal to negative 1. Now, trying to eliminate the x's, I'm going to choose to multiply the bottom by a negative 4. I'm getting negative 4x minus 20y minus 4z is equal to negative 28. Adding the two equations together, the x's eliminate, and I'm left with a negative 21y minus 2z is equal to negative 29. Now I need to use the equation we haven't used. Remember, we just used the first and the third, so I need to use the middle equation. And in fact, if I wanted to eliminate x again, I could leave that 2x alone and then multiply the bottom this time by a negative 2, and x would disappear once again. So I'm going to copy the middle equation exactly as it is, 2x plus 3y minus 3z is equal to negative 13. And now I'm going to multiply the bottom this time by a negative 2 to get a negative 2x, a negative 10y, a negative 2z, and on the other side that will be equal to a negative 14. Adding the equations together, x eliminates, and we're left with negative 7y minus 5z is equal to negative 27. Now we have two equations with just two variables. This one has a negative 21y. If I were trying to make the y's disappear, it would be nice if this were a positive 21y. So now performing elimination on these two equations, I'm going to leave that first equation with the negative 21y alone. And I'm going to now multiply the second equation by a negative 3 so that I will now have a positive 21y here. Adding the two equations together, the y's eliminate, and this time 13z is equal to 52. Now divide by 13 to see that z is equal to 4. Okay, once we have z, the next variable we need to find is actually our y, because we can use either of those two equations right there to find our y. I'm just going to go ahead and grab this one here, and I'm replacing that z with the 4 that we just found. So I'll have negative 7y minus 5 times the 4 is equal to a negative 27. Multiply first. 5 times 4 is 20, so it really says negative 7y minus 20 equals negative 27. When we add 20 to both sides, negative 7y is equal to negative 7. Dividing by a negative 7, we'll find y is now 1. Now when we're looking for x, we want to look at which of the original three equations looks the simplest. And when I look at equation 1, 2, or 3, 3 definitely looks like the easiest equation to me. So I'm going to grab that third equation. This time I need to find x, so I'll plug in the y, which we just found was 1, and I'll replace the z then with the 4 that we found back here. And I'll obtain x plus 5 times 1 plus 4 is 7. 5 times 1 is 5. Add 4 to that to get 9. So that really just says x plus 9 is 7. Now to find x, subtract 9 to see that x is negative 2. When we write our answers, we want to write them in order, x, then y, then z. So negative 2, comma, 1, comma, 4. Don't forget your parentheses. And your answer looks just like this. If we were lecturing in the classroom, this is the point where I'd have you try one on your own. So this next problem, if I were attempting to do it, I would have started by looking at the 3x here and probably multiplying the top by a negative 3 to make the x's go away. Then I would consider the bottom, and again, I would still just use the top and multiply by a negative 5 to make x disappear again. At this point in the video, might be best to pause and see if you can do that problem on your own. Once you've worked out what you think is your solution, go ahead and restart the video again to see my solution. As we discussed, I would have started by multiplying the top by a negative 3 to get negative 3x plus 6y minus 9z is equal to negative 15. I would have then left the middle equation alone. Now when I add, x eliminates, and I get 3y plus 10z is equal to negative 6. Now looking at the bottom equation with the 5x, I'm going to go back up to the top again, but this time I'm going to multiply everything by a negative 5 to get negative 5x plus 10y minus 15z is equal to negative 25, leaving the bottom alone, and now adding. X eliminates again, and now I have 11y minus 18z is equal to negative 22. Now we're looking at two equations with just two variables. So we're going to perform elimination on those two equations to find y and z. Looking at my y's, I have a 3y here and 11y here. So the number I'm trying to obtain is 33. I'll multiply the first by 11 to yield 33y plus 110z is equal to negative 66. Multiplying the bottom, or the second rather, by negative 3, I get a negative 33y, a positive 54z is equal to 66. Adding those together, the y's eliminate, and I'm getting 164z is equal to 0. 0 divided by 164, though, is just 0. Now I'm going to look at this equation here, and I'm going to replace that z with a 0. So that negative 18 times 0 is just 0. All that will be left is 11y is equal to negative 22. Dividing by 11, I'm finding that y is negative 2. Last step, we still need to solve for x. So look at the original equations. The top equation looks the easiest to me, and I'm going to go ahead and replace the y up here with a negative 2 and that z with the 0. Then I will have x minus 2 times negative 2 plus 3 times 0 is 5. Well, this 3 times 0 is 0. This negative 2 times negative 2 is a positive 4. So that just says x plus 4 is 5. Subtracting 4 from both sides, we find x is 1. Your answer, x, y, z, should be 1, comma, negative 2, comma, 0. Looks like this. Moving on, we want to look at those special cases that we saw where we would have no solutions because the lines didn't intersect, or we would end up with an infinite number of solutions when the lines were on top of each other. So let's go ahead and take a look at some of them that don't quite work out to be that perfect triple ordered pair. Up at the top of the page there, if we're trying to eliminate x and we're just looking at the first two equations, I would start by multiplying the top by 2 to obtain 2x plus 6y minus 4z is equal to 4. I'm going to leave the middle equation alone. Negative 2x minus 4y plus z equals 0. Adding those together, x eliminates, and I'm left with 2y minus 3z is equal to 4. The equation we haven't used is that bottom equation with the negative 3x, and I'm going to leave the bottom alone, and I'm going to use the top again, multiplying by 3. So the top would become 3x plus 9y minus 6z is equal to 6. The bottom, I'm going to copy just as it is. All right, adding those together, the x's eliminate, and we're left with 2y minus 3z is equal to 5. Okay, now we want to eliminate either y or z here. And notice that if we look at y, we have a 2y here. It'd be nice if this were a negative 2y. So I'm going to multiply that by negative 1. So the first equation, 2y minus 3z is 4. I'm leaving alone. The second equation becomes a negative 2y, a positive 3z, and on the other side, negative 5. Adding the two together, the y's eliminate and the z's eliminate. So on the left-hand side, we would have 0. On the right-hand side, 4 plus negative 5 is negative 1. So this time we get a statement that's completely false. 0 can never be negative 1. And remember, when we get a false statement, this is the case where there is in fact no solution. And our answer would just look like this. Let's go ahead and look at the next problem. This one's a little bit different. I would probably try eliminating x's in the first and the third equation to get started. So I would leave the top equation alone. That bottom equation, if I made that a negative 2, x would go away. So copying the top exactly as it is, I am obtaining 2x plus 3y minus 6z is equal to 4. The bottom is getting multiplied by a negative 1. Negative 2x minus 5y plus 6z is equal to negative 8. This time, when I go to add those together, x's eliminate and z's eliminate. And if I look at what's left, 3y plus negative 5y gives me a negative 2y. And on the other side, 4 plus negative 8 is negative 4. Dividing by negative 2, we've now found that y is in fact equal to 2. Well, how do we find z? This is not the same as the other problems that we've done so far. What I would recommend doing at this point is I would take the fact that y is 2 and I would plug that y equals 2 into any of the two equations that you see up here. Probably just grab the first one and the second one. In fact, in the first equation, if we replace y with 2, that 3 times 2 gives me a 6 right here. So the first equation would read 2x plus 6 minus 6z equals 4. Then, if we look at the second equation and also replace y with 2, 2 times 2 is 4 in the middle there. So that would say 3x minus 4 minus 9z is equal to negative 7. And this is a 2 by 2 system. There are just two equations in two variables, but it doesn't look quite like the 2 by 2s that we're used to seeing. It would be nice if we moved the constant over to this side in both of those equations. So that's exactly what we'll go ahead and do next. If we take that first equation and subtract 6 over to the right, 4 minus 6 would give us negative 2. So the top would read 2x minus 6z equals negative 2. On the bottom, we're adding 4. Now the left just has a 3x minus 9z. And on the right, negative 7 plus 4 is negative 3. And now this looks just like the 2 by 2s that we're familiar with. Now we're going to go ahead and try solving this 2 by 2. So I'm going to multiply the top by 3 to get a positive 6x, which means I'm going to multiply the bottom by negative 2 to get a negative 6x. Multiplying the entire top by 3, I'm obtaining 6x minus 18z equals negative 6. Multiplying the bottom by negative 2, negative 6x plus 18z equals positive 6. And this time, when we add them together, x and z eliminate. So I get 0 on the left, and on the right, negative 6 plus 6 is also 0. And this time I'm not getting that false statement that we saw in the previous example. So up here in the previous example, when we get something that doesn't make sense, there's no solution. Down here, when we're getting something that makes perfect sense, 0 equals 0, we know 0 is 0 all the time. This is the case where we in fact will have infinitely many solutions. And we can just write our answer like this when this happens. Again, we're at that point in the video where if you would like to try a problem on your own, you should hit pause. I would go ahead and hit pause at this time and go ahead and try this next problem here. And once you've finished, restart the video to see my solution. Okay, hopefully you've tried this on your own first. Looking at this problem, I would first consider the top and probably the middle, myself personally. I see this 3x here. I would like this to be a negative 3x. So I'm going to start by multiplying the top by negative 3 to obtain negative 3x plus 9y minus 6z equals 33. The the middle equation with the positive 3x we'll leave alone. 3x plus y plus 4z is equal to 4. Adding those together, x eliminates, and we're left with 10y minus 2z is equal to 37. Okay, the equation I haven't used, the bottom, 5x minus 5y plus 8z is negative 18. I'm going to leave that 5x alone. I would probably grab the top and just multiply by negative 5. So multiplying the top by negative 5, negative 5x, positive 15y, negative 10z is equal to 55. Now the bottom equation I'm going to copy exactly as it is. Adding the two together, x eliminates, and we're left with 10y minus 2z is equal to, On the other side, 55 minus 18 is 37. Okay, now we have a system of two equations with just two variables, and I would just leave this 10y minus 2z equals 37 alone. I would multiply the other by a negative 1 to get negative 10y plus 2z is equal to a negative 37. Adding those together, y eliminates and z eliminates to give 0. On the other side, we also have 0. And again, because we're obtaining that true statement here, when all the variables disappear, answer would be infinitely many.